Good morning, Dr. Das.
Good morning. Good morning.
Good morning.
Sir, Raju join. Okay. Good morning, Raju.
Very good morning.
Yeah.
Morning.
We'll wait for another 5 minutes. Okay.
Yeah.
To allow people join.
हाँ हाँ हेलो हाँ नहीं ऐसी वो इसके आपका ए है ना हॉल ए है ना हाँ मेरा हॉल बी है हाँ अभी शुरू हो रहे हैं ओके
So, Dr. Raju, there are 6 people
Yeah.
there in this session. So, please request them to share their PPT to the organizers so that if in any case due to networking something happened, so that may be presented from here itself.
Yes. I hope all speakers has shared the PPT. If anybody is not sharing the PPTs, kindly send it to organizers so that if any network issues are there, then it will be rectified.
From this session, we are waiting for 2 more PPTs presentations. We already received 4.
Okay.
Do you have PPT number 130 ID? Study uploaded.
I have also shared my
PPT sequentially.
Yeah, abstract 38, 78, 130, and 139 we received.
Dr. Busair, whatever not received, you tell their name only.
Yeah, can you please repeat which one you have received or not?
Dr. Das, can you repeat the IDs?
We will share the details in the chat box.
Yeah.
Okay.
So, Let us start now.
Yeah,
Dr.
Dr. Raju, so this is, I hope actually we have to also wait for other people to join, but now the speakers are here, so we can start. And Dr. Raju will be coordinating this session, and speakers and whoever, please also organizer provide the questions from YouTube, because this is live on the YouTube as well. So if there are any questions from the YouTube, you can post it here. They cannot directly interact here. So please, Dr. Buser will be, or Trishanu or Johnny may also paste the questions here. So after each lecture, Dr. Raju, so they will be pasting the question from the YouTube, or otherwise whoever directly putting questions, you can
Yes,
entertain
right.
them.
Yeah.
Okay. So Dr. Now it is up to Dr. Raju.
Thank you very much, Dr. Das. Welcome to all the speakers on the occasion of WMO Day. I wish a happy World Meteorological Day. So, as you know that today's sessions, each talk is given the 10 minutes for presentation and 2 minutes for discussion. Okay, I request all the speakers to stick on that time and complete their presentation within 10 minutes. Okay, then we can go for discussion for another 2 minutes. So, in the first talk, the theme of this, there are 3 themes are there. One is the field experiments and observational campaigns by 2 talks, and modeling of monsoon processes 2 talks, and subseasonal to seasonal prediction 2 talks. There are total 6 talks are there in these sessions. First, I invite Dr. Supriyo Chakrabarti. He is speaking on investigating the atmospheric carbon exchange processes in Northeast India using the eddy covariance technique. So, Dr. Supriya Chakrabarti, yeah.
Yes.
Please, please share your presentation and just give that presentation.
Yes. Yeah. Can you see my presentation?
Yes, yes. Can you keep the full screen?
Yes.
Yeah.
So is this okay?
Yes, yes, yes. Fine.
Okay. Good morning, everybody. I just like to start my talk. It is known that the forest absorbs substantial amount of CO2 from the atmosphere. The trees and plants interact with the atmosphere through mass and energy transfer processes, and hence they modulate the weather and climate system. As this cartoon shows, the plants absorb CO2 through the process of photosynthesis. At the same time, they release carbon dioxide through respiration. Additionally, they emit a substantial amount of water vapor through the process of transpiration. The spatiotemporal variations in CO2 exchange, the extent of environmental controls on the carbon sequestration, and their seasonal and interannual variations of forest ecosystems over India are not well constrained. The monsoon plays an important role in carbon dynamics by introducing varying effects of continental and oceanic air masses on CO2 exchange. The productivity on the land also changes drastically in response to the monsoon system, which again influences carbon dioxide uptake and respiration process. To address some of these questions, we are conducting GHG concentrations. They are isotopic and eddy covariance derived fluxes at a few ecosystems across India. So the title of my talk is Atmosphere Biosphere Carbon Exchange Processes in Northeast India using the eddy covariance techniques. Here I define the terminologies. Net ecosystem exchange, or NEE, is the amount of carbon exchanged between the atmosphere and biosphere. Negative values mean uptake of carbon and positive values indicate release of carbon to the atmosphere. RECO is the total amount of carbon lost to the atmosphere due to autotrophic, heterotrophic, microbial, and soil respiration. RECO is equal to the above ground autotrophic and soil respiration. Soil respiration may vary significantly across the systems, ranging from 30 to 90% of total carbon released. GPP is the gross productivity and is mathematically shown as below. The net ecosystem exchange is partitioned into two components, the photosynthetic component FA and the respiration component FR. These two components cannot be measured directly. Through some parameterization process, the NE is partitioned into these two components. It is to be noted that the individual components could be much higher than the NE value as shown here as the relative dimensions of this arrow shows. The carbon sequestration process are controlled by various parameters. These are solar radiation, air temperature, humidity, photosynthetic active radiation, vapor pressure deficit, rainfall, cloud cover, etc. Rainfall plays a dual role. For example, low rainfall can create low soil water, which can reduce the photosynthetic activity. On the other hand, very high rainfall produces deep clouds, which may limit the low radiation and hence reduce the carbon uptake process. This figure shows the eddy coherence tower established at Kaziranga National Park in Assam. This hosts several sensors such as infrared gas analyzer, 3D sonic anemometer, radiation sensor, weather sensors, etc. This sensor measures the CO2 emitted by the soil, and this is a GHG sensor which measures ambient CO2 and CH4 concentration and their carbon isotopic ratios. The black dots in this map shows the eddy coherence measurements carried out by different groups across India. Maximum carbon sequestration typically takes place during the monsoon season to late monsoon to early winter. However, Northeast India shows a different behavior. Depending on the meteorological conditions, the maximum carbon uptake takes place during the pre-monsoon season. The objective of the studies are what are the seasonal variation of any GPP and RECO, how do they compare with other ecosystems in India, how do we improve the partitioning of any into the components, and how the carbon and water cycles are linked together. These figures shows the various meteorological parameters. They are monthly variation. For example, the first panel shows the rainfall, and this is the temperature, and this lower panel shows the photosynthetic active radiation, and this right panel shows the leaf area index. One important and common feature is that during the pre-monsoon season, for example, LAI shows the maximum value, radiation is also high, and since this region gets adequate amount of rainfall, so this provides a conducive situation for enhanced photosynthetic activity. This plot shows a typical diurnal pattern of NEE at Kaziranga National Park. The maximum negative value is obtained around noon when radiation is high. The negative component is photosynthetic uptake as shown by this green arrow, and the photosynthetic positive component shows the respiratory release of CO2 as shown by these two red arrows. Please note that the positive component is reasonably high for these ecosystems. The right panel shows the figure shows the monthly variation of NEE. And the May month shows the maximum values, while the winter time is characterized by minimum values. The red portion shows the red portion shows the respiratory components. As evident in this figure, the total amount of respiratory release of CO2 is comparable to the amount of carbon uptake by the ecosystem. Here we have decomposed the NE into its two components, the GPP and RECO. NE is shown by blue dots, GPP is by green lines, and RECO is by red lines. It is to be noted that the relation between NE and its components yield only one equation, but there are two unknowns. So to better constrain these relations, we need another equations which can be used to better constrain the partitioning process. We have measured the carbon isotopic ratios of CO2, and which can be used as an additional parameter to constrain this equations. So this is what we have done, and this shows that this method provides may have potential to better constrain the two fluxes. As mentioned earlier, the heterotrophic respiration is significantly high in Kaziranga ecosystems. We quantified the soil carbon fluxes to get idea about the below ground and above ground respiration component. We have measured the soil CO2 fluxes from November 2019 to April 2020. The dashed line in this figure shows the RECO, or the total ecosystem respiration. The solid line is the NE for the respective months. The soil CO2 flux values are shown here by the stars. The soil CO2 during this winter is low, but it progressively increases from February and attains the maximum value in April. The right panel figure shows the monthly sum of above ground soil CO2 fluxes, and one notable feature is that these two components are quite comparable. These figures shows the effect of VPD on GPP, as shown here. Until a threshold value of VPD, GPP usually increases. For example, they're shown in this monthly and the seasonal value, but after a threshold value, GPP usually decreases. Here we saw the diurnal effect of rainfall on the effect of basically diurnal variability of rainfall. This figure shows the hourly count of rainfall, and the variation is plotted for two observational years, 2016 and 2018. Total count of daytime rainfall in case of 2016 was higher, as shown by the violet bars, while the total counts of daytime rainfall in 2018 is relatively lower. So as a result, 2016 acted as a net sink of net source of carbon, whereas 2018 acted as a net sink of carbon. We have also measured the precipitation isotopes. These figures shows the relation between the latent heat fluxes and the delta 18 of rainfall. The vapor flux measured by the eddy coherence technique is converted to latent heat fluxes. Water vapor flux, especially from the surface, emits a greater number of lighter isotopes. As a result, precipitation delta 18 shows an inverse correlation with the latent heat fluxes, as shown by these plots. This is caused by enhanced, but the pre-monsoon season, what is shown here in this panel, shows an opposite behavior. This is caused by enhanced plant transpiration, which releases relatively greater number of heavier isotopes. This is a unique result which shows a strong link between the hydrological cycle and the carbon cycle during the pre-monsoon season in these ecosystems. The coupling, however, is weak in other seasons. These figures shows the variation of GPP across India. What is shown here is that in case of Madhya Pradesh in Betul, which harbors a tip for it, shows the maximum GPP, whereas in case of Kaziranga, it shows significantly lower GPP than other parts of India. And here I summarize this talk. This figure shows the diurnal variation of any on a monthly time scale, as shown by this orange line, and this blue bars shows the monthly variation of rainfall. And as shown here, the maximum carbon sequestration takes place during the pre-monsoon time. The carbon sequestration process weakens in monsoon, and subsequently it gets reversed in winter. The respiratory components, for example, this positive components is significantly high in these ecosystems. On an annual scale, the Kaziranga ecosystem acts as a mild source of carbon. The increased productivity during the pre-monsoon season releases higher amount of heavier isotopes in oxygen and also in hydrogen, and which shows high delta 18 or delta T values during the pre-monsoon time. Thank you very much for your attention.
Yeah, thank you, sir, for timely completing your talk. Is there any questions? If I didn't find any questions in the chat box, is there any YouTube questions are there?
No questions from YouTube, sir.
Okay, right. So if there is no questions, let us thank Dr. Supriyo for his nice talk. Then we move further. Next talk is.
I stop sharing.
Pardon?
I have stopped sharing.
Yeah, thank you. Yeah, the next speaker, Dr. Ambuj Jha. He is going to speak on role of orography on the cloud and precipitation properties over the Western Ghats. So, Dr. Ambuj, over to you.
Thank you, sir. I will share my screen. Yeah, actually, I am facing some problem in sharing. So I have already shared my PPT to organizer. Can they
Can you please
help
share
me?
their Dr. Ambu's presentation? Yes, yes. Yeah.
Yeah. Yeah, thank you. Thank you for sharing. Yeah, so I am Ambujha. So I will be presenting on radar observations of spatial structure of precipitation in relation to orography over the Western Ghats of India. Next slide, please. Yeah. The Western Ghats, as we know, is a chain of run parallel to the west coast of India and is a chain of narrow coastally oriented mountains with complex topographical features. It forms one of heavy rainfall receiving regions in the tropics, which is why it is an ideal test bed for cloud and precipitation studies. Across the Western Ghats, spatio-temporal variability in clouds and precipitation exists. The knowledge of spatial patterns of precipitation over the Western Ghats is imperative for disaster management, water resources management, and understanding the orographic rain processes. Next slide, please. The spatial structure of precipitation over the Western Ghats is greatly influenced by the complex topographical features. Earlier studies, which are mostly based on satellite data and sparse in situ measurements, lack to provide high resolution spatio-temporal features of precipitation across the Western Ghats. Earlier studies based on infrared data actually showed that the rainfall maxima lies in offshore regions of the Western Ghats. However, recently, high resolution studies based on models or TRMM 2825 product high resolution data showed that the rainfall maxima is lying on the upslope region or immediate to the summit and not in offshore regions. So in this context, ground-based radars have great potential to resolve the features of clouds and precipitation at the scale of complex terrain of the Western Ghats. In this study, we attempt to examine the spatial structure of precipitation using ground-based X-band radar, which is stationed at Mandardev, a remote hilly location in the Western Ghats. Next slide. Yeah, so this slide shows the study region. The circle in the left figure shows the study domain, which is zoomed in the middle panel to show the topography of the region and the locations of two observational sites, MDV and HSEPL. MDV is radar site which is located at Mandardev, where two radars, X-band and K-band, are located. The radar site is shown in this figure where the two co-located radars can be seen. Sorry, yeah, the coverage of X-band, the inner circle here shows the coverage of K-band radar, while the bigger circle here shows the coverage of X-band radar. Another site is HACPL, which is High Altitude Cloud Physics Laboratory, which has an excellent suite of instruments for cloud and precipitation studies and for complementing the radar observations. A red dashed line can be noted here, which is actually the line of range height indicator scan of X-band radar, which is able to provide cloud vertical structure across the Western Ghats. Zooming further into topography, we can see the elevation profile along this dashed line is shown here, and the location of HSCPL and MDB site are marked. Next slide. Yeah, so in this study, we have primarily used X-band radar data sets, and for the period of June to September 2018, so mainly volume coverage data obtained from PPI scans, that is plan position indicator scan of radar, and range height indicator scans of X-band radar are used. In addition, impact distrometer data, which is located at HSCPL, have been used. Next slide, please. Yeah. So the spatial, now coming to spatial structure of rain. Yeah. So in order to obtain radar-based precipitation estimates from radar reflectivity, it is a normal practice to use ZR relation. So in this study, we have identified 4 precipitation categories, and corresponding ZR relations are obtained from by Das et al. 2017 over HACPL site. The four precipitation categories identified are shallow convective, convective, stratiform, and mixed convective. And the corresponding ZR relations are shown here. In this figure alongside, we can see the comparison between radar derived rain with the distrometer measured rain. What we see here is that the radar is underestimating rain in most of the cases. However, the pattern of variability of rain is having a good agreement. Next slide, please. Yeah, so this slide shows the spatial structure of rain amount and rain frequency observed within X-band radar domain. So, and the red curve here in the left figure, the red curve here shows the summit line, and there is and a beam blockage can also be noted in this sector of the radar. However, as we are concerned with the orographic influence of Western Ghats on precipitation properties, so this is not affecting much the objective of the study. So we can see here that the maxima of rain amount is is concentrated in a specific region here and is away from the summit. Similarly, rain frequency is also observed concentrated in a specific region and is away from the summit. Such spatial gradients in rain amount and rain frequency are can be provided only with high resolution observations and were not seen earlier with previous studies. Yeah, next slide, please. So this slide shows the maximum in rain intensity and shows the spatial structure in rain intensity and 18 dBz echo top height. So here we see that the maximum in rain intensity is actually located over ocean or sea and over leeward side, and also immediate to the summit line, which is the red curve. A minima in rain intensity is observed. The 18 dBz echo top heights also suggest that deep clouds over the ocean or coastal side and over leeward side, whereas shallow clouds are dominant along the summit line. So these features are mostly known that deep clouds are existing over ocean, which is producing high intensity rain, and shallow clouds are existing over the near the slopes or at the summit of the Western Ghats, which is producing low intensity rain compared to over ocean and leeward side. But what is not known is the why the precipitation maxima of rain amount is located at a particular region, concentrated in a particular region, which we observed in previous slide. So actually, so in order to explore better into the orographic influence of the Western Ghats on the rain amount, so we have a line of we have RHI scan. Can you go to previous slide? Yeah, thank you. So in order to explore that the orographic influence on rain amount, so we have RHI scan, which is actually passing through the maxima of rain amount and rain frequency. We have RHI scan along this dashed line. We attempted to explore the cloud and precipitation properties along this dashed line, which will give the variation in cloud and precipitation properties and also the orographic patterns which is influencing them. Yeah, so next slide. Yeah, go to next. Yeah. So this is the precipitation. This is the rain amount and rain frequency along the RHI scan across the Western Ghats along the dashed line along the line of RHI scan. So here we can clearly see that the maxima in rain amount and rain frequency is lying in the low is located in the low lying slopes and not at the summit. Uh, uh, our initial analysis suggests that basically the high elevation peaks and the cascaded mountains and higher width of mountain barrier here is actually causing higher rain amount maxima to be located in this region, which is not present over other regions within the radar domain. Yeah, next slide, please. Yeah, so the top figure here, top left figure here shows the distribution of 18 dBz echo top heights across the line of RHI scan, and we see a bimodal structure, bimodal distribution of 18 dBz echo top height of clouds in the right top figure here across the Western Ghats. We also see that the middle figure here shows the mean echo top height of 18 dBz radar echoes, which show that most clouds, most shallow clouds are occurring near summit, and deep clouds are occurring over oceans. Next slide, please. Yeah, so in order to better identify the influence of orography and on cloud and precipitation properties, so what we have done, we have demarcated the region along the RHI scan line into three parts: R1, R2, and R3. R1 is basically the ocean and covering the ocean and coastal side. R2 is on the slopes, and R3 is the plateau region. So over the R1, and we have obtained CFAD of reflectivity over all the three regions. So we see that deep clouds are existing over ocean or coastal side, and over R2 and R3 regions, comparatively relatively shallower clouds are present. However, the modal value of reflectivity is found at 20 dBz and is located between 3 and 4 kilometer altitudes. And also in bright band increasing proportion of stratiform rain is found over the R2 and R3 region, which is shown by this prominent signature of bright band between 5 and 6 kilometer altitude. Yeah.
Dr.
So
Ambudh, can you summarize? No.
Yeah. I'm coming to summary only. Yeah. Yeah, so our observations are show that the maximum rain amount and rain frequency are concentrated in a specific region away from summit. The maximum rain intensity and 18 dBz echo tops are in offshore region and leeward side in agreement with previous studies. Bimodal distribution of 18 dBz echo top heights located along the slopes. Most shallow clouds are occurring near the summit. CFATs show deep clouds occurring over the ocean with modal value of 20 dBz between 3 and 4 kilometer altitude. So in our next stage of analysis, we are investigating orographic factors in a detailed manner of like elevation, slope, width, etc. to understand the influence of orography better. With this, next slide, please. Yeah, I would like to acknowledge Director IITM, HSCPL, and Radar and Satellite Meteorology team members and IWM-7 organizing members. With this, I would like to next slide, please. Thank you for your time.
Thank you, Dr. Ambudh, for nice presentation. In your previous slides, you have shown the radar estimated precipitation, right? One of the frequency. So, have you compared anything with the ground truth observations, like?
Right, sir. We have compared. That's what I showed. The ZR relationship obtained using radar. We have compared with the distrometer rain measurements.
Okay.
And we found that yes, radar is underestimating rain because of the variability associated with ZR relation with DST characteristics. So, but the pattern of variation is having a good agreement.
So, how we are going to correct with bias correction with the radar estimated precipitation? Is there any correction you are applying, or?
Yes. So actually, the radar estimated rain is providing rain at actually 2 kilometer altitude. So, and we are comparing with the distrometer at ground. So basically, we in the next stage, I plan to extrapolate that rain to the surface, and also we are planning to use a network of rain gauges from other departments, so which will be used to thoroughly means correct and impose and better provide the estimates.
Yeah, thank you, Dr. Ambos, for nice presentation. I think there is no questions posed in YouTube and here, so we are going for move to next presentation. The session is theme of this next talk is modeling monsoon processes. I invite Dr. Saket Sengupta. Please kindly upload your talk. He is going to talk on assessment and bias decomposition of isotope-enabled general circulation models for Indian summer monsoon and their implications to paleoclimate modeling.
So is my slides are visible?
Yeah, over to you. Yes, Saket. Thank you.
I'm audible also.
Yes.
Okay, so good morning all. This is the topic of my talk and these are my co-authors. So I'll be talking on the assessment and bias decomposition of the isotope-enabled general circulation models on Indian summer monsoon and their implication to paleoclimate modeling. Before going into the details, just one or two slides for brief introduction of what is water isotopes. We are all familiar with the term heavy water and light water. Heavy water means the water which comprises the heavier isotopes of hydrogen and oxygen, and lighter water is which comprises of lighter isotopes of oxygen and hydrogen. So whenever some phase changes occur, say from water to vapor, the heavy isotopes prefer to go into the heavier phases, the lighter isotopes prefer to go into the vapor phases more. So this results a change in the heavier to lighter isotope ratio in the water and vapor, the process which we know as isotope fractionation. So this causes large heterogeneity in time and spaces. So this figure shows that what are the different processes through which the isotopes can be fractionated in hydrosphere. So these are some processes that shows how the isotope values changes. So now the isotope and rainfall amount, isotope and its relation with temperature, or isotope and its relation with moisture circulation, these are used for paleoclimate reconstructions also. Now we know a little bit about what are isotope-enabled GCMs and how do they work. Isotope-enabled GCMs is actually a GCM which simulate water isotope ratios 18:16 and D/H of precipitation, considering various physical processes that I showed in the previous slide, which is occurring in hydrologic cycle. In a very simple way, the isotopes in general circulation model is a combination of an atmospheric GCM plus several isotope parameterization schemes. So these isotope parameterization schemes, they take care of all the fractionations that is going on, which I showed in the previous slide. So together all this, we ultimately get a simulated product of the isotope ratios. So it incorporates water isotopes as a conservative tracers. Whenever water phase change takes places, isotopic water behave differently with the ordinary water, and this property is being used in these models. Thirdly, how reliable are these isotope-enabled GCMs? You can see it is a plot of global compilation of the observation and model data, and one can see that these correlations are very high. It is for 0.84 to 91 in case of annual scale and 0.75 to 86 in case of seasonal scale. But still, these models have many lacunae. Number one, this model isotope biases are very large over the extratropical region. Secondly, the vapor isotopes over the marine boundary layer is very poorly simulated in most of the models. Especially in India, the comparison of these models work is very scanty. The one paper which published here I showed, they used climatological monthly mean data, and they showed only over the isotope region, they find a good correlation between the isotope enabled circulation model generated rainfall and observed rainfall and their isotope values. But the information which we lack here, that we need to know the variability, how the models capture the variability in a seasonal scale, especially during Indian summer monsoon, because this monthly variation is often required for the comparison with the proxy data. And second thing what we lack is which factors control these isotope biases and how much. It is better if we can provide a quantitative decomposition of the biases related to various physical processes in these models. So keeping this in objective, we did the study. So these are our study locations where we have long-term isotope datasets already generated, and it is available in the websites. So these are our observed data based on some homogeneity in the moisture source, rain mechanisms. These stations are actually grouped into 3 sub-regions: West Coastal India, Eastern Coastal India, and North India. And these are the models that we have used. I'm going a little bit details into observation and model data here. These are the specification of the models that we use for the study. So there are total 5 models and 3 NAJ models that we've used. This is their resolutions, and this is the data period of availability. Compared to that, this is the observations. So we have used here 2 kinds of observation. Number 1 is the monthly average rain isotope data, which is available in the global network of isotopes in precipitation. It is a project under International Atomic Energy Agency. And secondly, we have taken vapor isotope data from tropical emission spectrometer. So here we obtain the vapor HDO and H2O. So it basically gives the hydrogen isotope data. So it is available for 17 pressure levels. So that we also took. And this observation and model isotope data from these stations for all summer monsoon months and of the synchronous time periods are marked as per the sub-region that I already told, and the biases are estimated. So now see our results. So this is, you can see that we have plotted the oxygen isotope variations, hydrogen isotope variation, and another factor we call DXS, which is derived from hydrogen and oxygen both, which actually takes care of all the fractionations, most of the kinetic fractionations that is occurring in the hydrologic cycle, which I showed in the previous, for the first slides. So you can see that the oxygen isotope values, these are underestimated in West India, and East India it is marginally underestimated, but there is no systematic trend that we found in the Northern India. Some models overestimate, some models underestimate. So on the other hand, this DXS parameter which I explained, these are reasonably simulated in West Coast India, but not for other 2 regions. As far as the correlation between the observed and model monthly data are concerned, some few models, few free models show some correlation, but generally we don't find any correlation in the NAJ models. So as I told earlier, that the rain amount isotope correlation is an important correlation which is often used in the paleoclimate reconstruction. So we just try to see that how the models capture this correlation vis-a-vis observation. So we can see that this GNIP is the observation. So most of the cases observation do not show any correlation in any of the sub-region, where few of the models, they show very high correlations. So observed, some models do show that amount isotope correlation, but models do not. Now the question arises that whether these models is showing some correlation, observation not showing, whether this causes any, this rain isotope biases is actually whether controlled by these rainfall biases or not. In order to check that, we plotted rain bias and rain isotope biases. You can see that out of all these models for 3 different regions, very few cases, so these are the 4 cases when we found a negative correlation which is expected between the rain bias and rain isotope bias, suggesting that this possibly for only these models, the isotope biases may be controlled by the amount biases. But the isotope biases is not solely controlled by the rainfall biases for most of the models. Although for those models which show significant isotope amount correlation. Now we will explore that which factors control isotope biases across models. So you can see that here also we plotted the mean biases of different models together for different cases. Only 3 occasions we get some correlation, otherwise there is no some general trend. So this suggests that the multiple parameters simultaneously control the rain isotope biases and which vary from model to model. And secondly, these are all the local data that we have used, that isotope data and meteorological data from the same station. So possibly the another possibility is the isotope biases in a given region may be actually controlled by the physical fields in the other region. In order to check that, we have actually plotted the spatial correlation of the biases. Here we have considered 2 stations which has more co-located data sets with most of the models. One is Kozhikode and another is New Delhi. So this is the humidity and vertical integrated moisture transport biases that is shown here, and we found a very strong correlation at New Delhi. It is a negative correlation between the VIMT and humidity both. We got the same correlation for rain and wind biases also, which I have not plotted here. So it clearly indicates, which is expected, that whenever there is it is a underestimation of the rain. So whenever there is underestimation of rain in the Bay of Bengal moisture trough, we get a high positive biases of isotope values over the New Delhi. So this is our findings. Next, actually, we tried to do a little bit more. We wanted to see that how much biases is actually contributed to the model in different processes. In order to check this, actually, we compared the vapor and rain isotope data over the 4 different instances. In first instances, we compared the observed and model vapor isotope data over the surface level. Secondly, between 1000 to 600 millibar, how observed data changes and how model data changes. Thirdly, along the moisture transport. For this, we chose only the station Kozhikode. So this is all about Arabian Sea, where from the moisture is coming. So from 2 to 3, it is the moisture transport at 600 millibar level. And fourthly, we estimated the rainfall isotope, rain isotopes at the cloud base and compared it with the same at the stations observed data. So these are the 4 instances where we compared the isotope values to know which processes is dominantly controlling the biases. So first we compared the vapor over the source region. You can see, excepting this one model, most of the models reasonably simulate the surface level vapor isotope values, which indicates that model captured this process nicely. Secondly is the differences between the surface and 600 millibar. Here we get a lot of variation in the model, and this most of the some models overestimate, some models largely underestimate the value, which clearly indicates that model actually could not simulate properly the mid-tropospheric mixing processes that is occurring here and which is causing a huge biases. So in the third process, we wanted to see how the biases takes place from Arabian Sea to the locations. Here we plotted the longitudinal variation of the isotopes, and accepting this one model, isotope enabled general circulation model NAST, most of the model simulates actually quite well the longitudinal variations, which is matching very nicely with the observations, and therefore no additional biases we can see is contributing in this process. Now we come to the last process, that is the last 2 processes, that how the biases are there in the raindrop evaporation. For this, we estimate raindrop evaporation from the rain isotope values at the cloud base that we estimated and compared with the rain isotope measured at the observation. From these 2 values, we compute the raindrop evaporation fraction. The same thing we did for observation, the same thing we did for all models, depending upon their available outputs. So when we compare that, we find a very strong correlation across models, which clearly indicates that the model which is estimating evaporation higher is the model which is showing high isotope biases. We further explore that how much the biases is coming from the stratiform rain fraction. For this, actually, we estimated stratiform rain fraction from the model, as well as we compared that with the observation. While the people have reported a strong negative correlation between stratiform fraction and Day-2, we got an opposite trend in the Day-2 and stratiform rain biases, which clearly indicates 2 things. Number 1, the models possibly could not simulate adequately the stratiform rain fraction, and secondly, it fails to, or it doesn't simulate properly the isotopic fractionation related to the stratiform processes. So when we compile, I'm coming. So when we compile all the processes, we can see the major factors which is contributing to the biases is the mid-troposphere mixing processes or the vapor isotope values. There is a large changes, and secondly is the raindrop evaporation. So this contributes, we calculate almost 80% biases in those models. So we conclude that the efficacy of the models mainly depends on how proficiently the models capture the mid-tropospheric mixing processes, and secondly, how proficiently it estimate raindrop evaporation. Thank you.
Okay. Thank you, Dr. Sengupta, for the nice talk, and there is no questions posed here. So thank you very much. We'll go for next speaker. I invite Dr. Daniel Simon. He is going to speak on boreal summer intraseasonal oscillation convective initiations in S2S reforecast. Dr.
Yes.
Simon?
Yeah, can you hear me?
Yes, yes. Please upload your.
I'm not able to share because Dr. Sengupta is sharing.
Yeah, please unshare, Dr.
Just a minute.
Yes.
The center top, you can move your cursor there, then one panel will come down, you can see stop sharing option.
Stop sharing. Okay.
Yeah.
Yeah, thanks.
Thank you.
Can you see now? Hello.
Yeah. Can you please upload your presentation?
You can see my presentation? No.
Not yet.
You can see, right?
Not yet.
Hello. Not yet. Okay, okay. 1 second. Yeah, can you see now?
No. Maybe admin can share your presentation. Is there with admin?
Yes, it's there, it's there. I'll try once again if it's okay. Yeah, can you see now?
Yes.
Okay, thank you.
We can share. Go for full screen. Yes.
Yeah, is it clear now?
Yeah.
Okay.
Please be timed 10 minutes.
Yeah, sure, sure. So title of my presentation is Summer ISO Initiation and Propagation Features in S2S Models. So I'm Daniel. And so a bit of introduction first. The intraseasonal oscillation convective initiation refers to the transition of shallow convection to organized deep convection. And here is a animation showing how the summer ISO propagation looks like in the precipitation field. And previous studies shows that this summer ISO is closely linked with the active and break phases of ISM. And hence it's quite important to understand it. And yeah, so now coming to the precursor signals associated with the ISO initiation. So previous studies reported that the moisture buildup, temperature warming, and vertical velocity buildup are the few precursor signals associated with the ISO initiation. Now, there are various mechanisms proposed to explain this ISO initiation. One is that an ISO initiation, preceding ISO event can lead to another ISO event. Another is recharge discharge mechanism. And studies also shows that the oceanic processes can also eventually lead to ISO initiations. And yet another kind of mechanism suggested is the extratropical force. Now, coming to the ISO prediction skill. So here is a diagram showing the comparing the summer and winter ISO skills in the S2S models, and we see that in all the models, the summer skills are relatively less compared to winter skill, and the summer skill ranges from about 1 to 5 weeks. And we can also previous study shows that the primary ISOs are less skillful than compared to secondary ISOs. And also previous studies, for example, Kimetal 2010, they showed that the ISO initiation is relatively poorly represented in the models which they considered in their study. So with this background, I'll come to the questions addressed in this study. So one is how skillfully we can predict the ISO convective initiation, and how does that compare with the ISO further evolution skill? And also whether this ISO propagation skill has got any link to the background moisture field. So in order to address this, we make use of the reforecasts available from 10 models which are participating in the sub-seasonal to seasonal prediction project. And 6 out of 10 of these models are ocean coupled. Now coming to the ISO, summer ISO, we focused on one more thing is we focused on the summer ISO to focus address these questions. So here are the so we used the Euler MJ index, which captures the convective features and the seasonality of ISO to identify the ISO initiations. So it is the criteria used. So we use the OMI amplitude should be greater than 1 over phase 1 and 2, and also it should show anticlockwise rotation with amplitude greater than 1 for at least 5 days from the initiation time. So we identified such 62 cases, and here are the cases represented in the phase space diagram. Now here is a lead lag composite of the oil intraseasonal filtered oiler with respect to the ISO initiation days identified. So we see that the convection suppressed state switches to slight convective state by the initiation day, and further it strengthens and propagates simultaneously in the eastward and northward directions. Now coming to the first question, which is how the models predict the evolution from the initiation. So the left panel shows that, and we see that the skill ranges from about 13 to 24 days, and the evolution skill is best captured in the UKMO model, and it is worst in CNRM. Now coming to the initiation skills, so we focused on only those models which have sufficient number of initiation cases, and there were 6 models, and we see that the initiation skill ranges from about 5 to 18 days, and the initiation skill is highest in CMA, whereas it is lowest in HMCR. Now here is a comparison of how the initiation and evolution skill looks like in terms of when the bivariate correlation drops to 0.5. And we see that the initiation is relatively poorly represented compared to the evolution skill in 5 out of the 6 models for which we have the initiation skill. Now further we looked into the eastward and northward propagations following the identified initiations, and here is a composite of how the eastward and northward propagations looks like from the initiations identified. We can see that in the UKMO model shown on the top right panel, the model captures the eastward propagation as well as the phase speed as well as the convective strength relatively realistically. And also, whereas in case of northward propagation, we see that the phase speed is more or less captured, whereas the convective strength is relatively deteriorating compared to the observation. Now, similarly, for all the models, we look the 2-week eastward and northward propagation in the Hobela diagrams, and then the pattern correlation is shown on the left panel. So we see that in individual models, the eastward and northward propagations are kind of comparable, except HMCR, which shows kind of more skill for northward propagation. And also we can see that the UKMO captures both the propagations relatively better, whereas HMCR and ECCC shows they perform worst in terms of the northeastward and the northward propagations respectively, and both of them are not ocean coupled. Now so previous studies showed that the moisture is quite important for the ISO propagation, and here's a scatter diagram showing how the ISO propagation, summer ISO propagation skill is linked with the summer mean moisture over the ISM domain using multi-model simulations. And also previous studies showed that this horizontal advection of the mean moisture by the tendency, horizontal advection term dominates the moisture tendency term, and in fact this term, horizontal advection term, is dominated by the advection of mean moisture by the intraseasonal circulation. And this is tested in few the S2S models, and Lim et al. 2018 showed that in fact the zonal moisture gradient is closely linked to the mean ISO propagation. So we looked into the summer lower tropospheric moisture distribution further, and as shown in previous literature, we could find the moisture maximum over the northeast India extending towards the Western Pacific, which is kind of captured by ECMWF and HMCR, whereas models like UKMO underestimate this, and for remaining models such as BOM, ECCC, and all, they either overestimates the magnitude or the zonal extent of this moisture maximum band. And a few models like CMA and HMCR, they kind of underestimates the moisture over the maritime continent region. Now we picked 2 regions, 2 boxes over the maritime continent and the Western Equatorial Indian Ocean, and checked with this question in mind, that is whether the zonal moisture gradient, background zonal moisture gradient, is linked to the summer ISO eastward propagation. And we in fact see a good significant relationship between the two across the models. And So, and in fact, we see that majority of the models, they underestimate this zonal moisture gradient. One thing to mention, the observed zonal moisture gradient is shown by the vertical dashed gray curve, gray line. And so we see that majority of the models are underestimating the zonal moisture gradient. And so, considering a worst performing model, so the zonal moisture gradient, background moisture gradient is weaker in this model. And for example, HMCR shown by this green, dark green dot. And in this model, if the advection of this mean moisture by the intraseasonal wind will be weaker, and which leads to weaker eastward propagation and hence weaker eastward propagation scale. So now coming to the summary. So we studied the summer ISO initiation and evaluation skills and quantified the skills in the S2S models, and also looked into what are the limiting factors, and how they are related to the propagation skills. And we see that the Indian Ocean BS ISO convective initiations are underrepresented related to its further evaluation skill in 5 out of 6 S2S models. And we see also that the 2-week eastward and northward propagation skills are comparable in individual models, with UKMO capturing the convective strength and propagation features most realistically. And we also see that the summer ISO eastward propagation in S2S models are closely linked to its ability to capture the zonal moisture gradient, and majority of the models underestimate the same. Thanks.
Yeah. Thank you, Dr. Simon. Any questions on this group?
I have a question. This is Mohan from NCMW.
Yes, yes.
Hello. Nice talk, Simon. I have a few questions.
Yes.
One thing is that in your models, that S2S models that you have considered, said there are coupled models, right? Few coupled models.
Yes, yes.
Have you looked at the SST and rainfall lead lag relation in those coupled models?
No, we haven't looked into the rainfall or the SST. Yes, we haven't looked into those parameters.
Because why I'm asking is that because this ISO propagation characteristics or the evaluation of these S2S subseasonal variability in the models, the operation process are very important. Okay, so that's one thing. And another question is, in your northward propagation of these models, have you looked at the shear and vorticity conservation? I mean, like there is a work by Binwang who has shown the ISO initiation on the equatorial Indian Ocean and then moves to poleward based on the shear and vorticity. I have not seen in the literature that you mentioned in the slide. So have you looked at that?
So the shear thing, that currently we are working on those things, whether the shear has, whether these models also show any link with the shear. So that we are currently working on. And the other part, vorticity, we haven't looked into. That is something which, but one problem which arises in this model is because these are like on the subseasonal to seasonal time scale. So these models are like 30 to 60-day runs. So filtering becomes a question to capture the intra-seasonal signal. So when we look into those things, so yeah, but of course, thanks for those questions. I'll of course try to address them.
Finally, last question. When you look at the horizontal advection term and you decompose the horizontal advection terms into its parts, like mean and perturbation parts, you're saying that it is because of the anomalous winds that is acting on the climatological moisture and the climatological moisture that you found on the northern part of India, right? So in the S2S signals, have you looked at the sources of these moisture gradients? Have you looked at the sources? Why the tendency term is lagging behind the advection term?
Yeah, so one thing to point here. So like we haven't looked into the moisture budget as such. So what we looked is like the mean moisture gradient and how it is linked to the propagation skill, and that is just an explanation which I gave.
Because why I'm asking is that because in S2S signals, some of the signals has some models in the model that you have considered in our analysis, we found that the ANSEP has a tendency to show the maximum contribution from the climatological winds acting on the anomalous moisture. So both the terms has their contributions. So just have a look at it so you can get the skill properly.
Right. Oh, thanks for that suggestion. I will try to look at that. Okay.
Fine. Thank you. Nice talk.
Thanks so much.
Thank you, Simon. We are going for the next. You can please unshare your presentation.
Yes, yes.
So that next speaker is Dr. Subodh Kumar Saha. He's going to speak on prediction and predictability of the seasonal Indian summer monsoon rainfall. Dr. Saha, please.
Good morning. Can you see my slide?
Yes, yes, you can go ahead.
Good morning to all of you. First, I would like to thank my collaborator, Samir, Anupam, Emma, Asrul Rahman, Archana, Yasas, and Professor Goswami. So let me begin with some of the very fundamental things on ISMR prediction and predictability. We know that this is from pioneer work from Chani and Shukla.
Audio is not clear. Can you keep your mic close? Yeah.
Yeah, now? Is it clear now?
Yes, yes.
So the basis of seasonal prediction is from the pioneer work from Chani and Shukla. We have shown that that the seasonal prediction is possible, and this is influenced by lower boundary, slowly varying lower boundary conditions. And also we know that ISMR seasonal mean or seasonal anomaly rainfall is nothing but a cumulative effect of all the events which takes place on the seasonal time scale, the synoptic or interseasonal, all those things. So they all together make the seasonal rainfall. Okay. So our hypothesis is that any predictor which is affecting ISMR anomaly, it must affect the subseasonal component, because the subseasonal components are the building block of the monsoon. Okay. But in general, what we see in the from previous studies, which literature, that those synoptic and subseasonal components, they are considered as a noise in the context of seasonal ISMR prediction. So let me show you some estimates from previous studies. There are some estimates that what would be the limit of ISMR predictability. Predictability means what is the what we can get maximum from a system. So that is the limit. Or other way, the ability of the system to be predictable is called predictability. So from Kumar et al., they use 2005 they use Demeter model, and they have shown that time the actual speed rate, when you see the blue line, was actually negative. And they have also estimated potential limit of predictability based on model, which is around 0.65. Now, next generation model, they have shown that model has improved. You can see the blue line, green line. The speed has increased. It's of course now is positive, but the potential predictability limit is around 0.65. And there are also some studies, US studies, which have shown that the limit of predictability is around 0.65. Now, another important point is that, as I mentioned, the subseasonal component is important for monsoon. But what we see in models, I'm showing a CB5 model, that they have a problem in simulating rainfall distribution. So model, all models, they show a large number of very highly salient and underestimating the intense rainfall. That means they have a serious difficulty in simulating subseasonal component. So the question is whether it is possible to have a high prediction speed with such a model where we have problem in subseasonal simulation. So with this background, I'll move on with our work, which I will summarize in few slides. We have 3 papers which we have published, and I'll try to summarize very quickly. So we have used a CFS model, and we have done 30 years of a handcast with 4 versions of model. And also we have used 119 years of observations, several observations. to estimate the prediction skill, predictability, and all the relationship. So let me begin with the final result of the in the form of skill, model skill. What I am showing here is a skill, perfect model skill, perfect model correlation, and that is the predictability limit, where each example is correlated with other example. Another way people estimate is the ANOVA, analysis of variance method, which is shown in blue dot, and red dot is the actual skill. We have 4 versions of model, Quant, Snow, and PHY, SNLP. All the version of model has a different improvements. So what you see here, that in some of the version model, we have actual skill more than the potential skill. So how this is possible? We know that the potential skill is the maximum limit, and we expect that the model skill will be lower than that. So why it is why this the behavior model is showing the paradoxical behavior? Then the question arises whether ISMR is predictable beyond this conventional limit, but we know the potential predictability. If so, what is the actual limit? And not, if it is not, if it is 6.65 upon 7 is the potential limit, then we have already reached the limit. We have a skill around 0.627. So whatever you do, that means whatever you do, whatever development you do, whatever estimation you do, there is no hope. You cannot improve for the forecast. So is it the case? So we see it is other way around. I'll show you. First of all, the potential predictability estimated is based on perfect model consideration. That model is perfect, and all these measures are based on model simulation. There is no binding relationship with observation. So we try to with a measure, try to have a new estimate which will have a binding relationship with observations. How to do that? The basis is that when you use a set of initial condition, you end up with some speed. If you have a different set of initial condition with same model, you end up with a different speed. So why don't you use all these skills in a systematic manner to estimate what the maximum skill you can get given the prediction system, given the assimilation system. So to do that, we have used the following method. We have a 16 number of examples, and now we make a combination, all possible combination of this example member. For example, if you have 6 example member out of 16, that is subset of 6 example, and make a correlation of example number of 6 with the observation. So by doing this, you get a distribution of correlation. And what I am showing here is the maximum and minimum correlation from each of the 4 models. So red line, you can see the best model we have, which we had a skill of 0.7, and which is showing that you have a skill more than 0.8 for 6 to 8 examples. So remember, these are all actual skill. So you can consider this is the maximum skill a model can achieve. Although this is not possible to achieve in practical, but this is the maximum limit one can get if you have the right kind of IC. Okay, so this we can turn we can consider as a maximum predictability limit of the ISMR by this prediction system. Now coming to the other point, that how subseasonal component is related with ISMR prediction and predictability. So earlier studies have shown that they are noise, but we found that there is an interesting relationship. This is the correlation between subseasonal variance with ISMR anomaly for several bands. For example, if you are x-axis is a periodicity, if you are say 12 days, so that means less than 12 day subseasonal variance correlated with ISMR. Here a skill of around 0.3. What you see here is correlation of subseasonal variance with India rainfall or central India rainfall. Both are quite similar, and you have maximum correlation on synoptic bands, which is around 0.6 or 0.65. So that tells that the lows and depression, they have a maximum contribution to the internal variability of ISM. Now comes the second band. This is sub 10 to 20 days, which is a moderate, and meso band, which is a lowest correlation with ISMR anomaly. Now, next question would be whether they are predictable. To show this, we have correlated with ENSO, because ENSO is the one with the largest predictor of the ISMR. So, what you see is it is also strongly related in the synaptic band as well as 10 to 20 days band. So, subseasonal components are really not noise, but they are a source of ISMR, seasonal ISMR predictability. I'll show you in detail in these two bands. We have a synaptic band and 10 to 20 days band, how the correlation between subseasonal variance and SST looks like. Over ocean, it is a SST, and over land, it is 2 meter temperature. You can see less than 5.2 days, we have a very strong correlation over answer region. And also 14.6 days, we have very strong correlation. These correlations are much stronger compared to what you get from correlation between ISMR and the SST. So that tells that these are the subseasonal components of the signal, not noise. Now, obviously, we got some comments, because what we have shown is the opposing view of some of the groups. So their argument, we have also replied. Their argument is that the peak correlation what we get in synaptic band is due to area average. We change the area, we change the domain average, we will change it is sensitivity domain. And the second point is that the mean and variance are positively correlated because we have a gamma distribution. Of course, we don't agree with this. And what we show that the synaptic systems, here you can see the track of depressions and cyclones. They all go through around the northern India, from there, mostly from Bay of Bengal, and then they cover a large distance. So, in order to capture their influence, you need a large area, large domain, sufficiently large that will be comparable to the scale of the system. So, what is the scale of the system? It could be Central India or all India. If you take a smaller one, that you may miss some of the system. For example, in 97, let's see 97 example, we have some 5-6 low ground depression. And if you take the area average, it looks like this line plot. So you have a D1, D2, D3, all the depressions it is able to capture. When you take area average of Central India or India, you can see the peaks are indicating the depressions and lows. So it is able to capture all the systems. It's not going to be.
Saha, can you please conclude?
Yeah, I'll come last. So the point is, you need to have a sufficiently large domain to capture those variability. And if you look in the last 100 years simulations, 100 years observation, so there is a strong variability between the relation between subseasonal and seasonal anomaly, subseasonal component and seasonal anomaly. And if you look how they are related with predictors, they are strongly related with predictors like WMO, PDO, all those things. So we try to also estimate how the predictability we can estimate from whether we can estimate from observation. So observational estimates also suggest that predictability of ISMR would be around 0.8 or so. So we try to put all these findings in a cartoon diagram, which is shown here. That the giant octopus is a intelligent predictor, which consists of all these predictors and trying to modulate the subseasonal component. So it appears that ISM is a highly predictable system. So I leave it there. Thank you.
Yeah, thank you, Dr. Saha. Any questions in this group? Okay, if there is no questions, so let us thank Dr. Saha for the nice presentation. So, can you please unshare the screen? We'll go for next speaker, Professor Virendra Goswami. Welcome, Professor Virendra Goswami. He's a former Vice Chancellor, and he's going to speak on a study of dynamical and morphological characteristics of the mesoscale convective systems to develop Thunderstorm numerical weather prediction models. Sir, please upload your presentation.
Okay, I just do it. I share. Can you see my presentation?
Yes, sir. Yes, sir.
Oh, okay. Thank you very much for training me.
Please put to full screen mode, sir.
Yeah, you see, I quickly try to finish it and go through the slides because already I have set about 20 minutes and I can't sit more than half an hour at a time. The reason being I'm suffering from spinal stenosis. It's my apology to every viewer who is there if I am not very clear when I am talking to you. Anyhow, well, today I am going to present you, as Professor Raju told me, study of dynamic and morphological characteristics of meso-scale convective system to develop thunderstorms models. You see, this is not a very new topic, and a lot of work has been done on thunderstorms. But and also the models have been also developed on the thunderstorms. But to develop the models, we try to give a new innovative hypothesis. That is, there are two hypotheses which have come out, which we worked in the University of Wisconsin long back, and with Professor Siomi, Martin, and Sigler, while I was working with them in the NASA Space Laboratory, Space Science Engineering Center. So we were the first pioneer to study the cloud cluster studies on the Bay of Bengal, rather a very big area, South China Sea, 120 degree east to 90 degree west, or up to Arabian Sea, covering the area of 15 to 10 degree north to 30 degree north and 10 degree north. So we were quite lucky to have the satellite pictures, which are not generally available. That is Defense Meteorological satellite pictures, which was shared by US Air Force to my professor. And on that, we worked first time over this cluster. Though the gate clusters were quite known long back and widely studied by Professor Sigler, Martin, and these people, but they were almost nil studies. I'm talking in 90s over the places of Bay of Bengal. Well, later on, this study of the cloud clusters, which have already published in the Monsoons in 90, which you can go through, we extended this work using the geostationary satellite, because those were the polar orbiting satellites, and also we worked on the Taurus satellite at that time, because in that time, INSAT was not available, I'm talking. So we worked on the polar orbiting, and this DMSP was very good. Visible reason, it is like X-ray film, and you can really manually count the cloud structure. I won't elaborate what are cloud structure. All learned August audiences here, and they know how to analyze the cloud clusters and through the satellite imagery. But for the detailed studies, we're done by using the McIDS. Well, now slowly I'll come on the other slides. And now the efforts is being made to develop the numerical prediction models, medium range weather forecasting models of this meso-scale convective activities, mainly thunderstorm. At the same time, also to extend the work to develop a numerical prediction model of thunderstorm using the giant cluster theory and the cloud clusters coalescence theory.
Sir, your slides are not moving. Can you please put the full screen mode, sir?
What is it?
Can you keep your slides full screen mode?
Full screen.
Presentation mode. Presentation mode. Bottom right, you can click here.
So the issue is started from the during sharing the screen. Actually, instead of sharing the presentation, you need to share the screen. Then only the slides will come in the full screen mode. So I suggest you to unshare and share again.
Oh, how to do it? I just.
Yeah, center top. If you move your cursor.
Otherwise, bottom,
yeah,
bottom there is a.
It is share is there on the top, and then admin IMB speaking and Subodh is coming. Just a minute.
Sir, you unshare it first. Go to the center top.
Okay.
Then one cursor will come down. Center top, sir. Center top. Cancel this. Go to the center top. And one panel will come down.
Share.
Not that one. Center top.
Okay, share. Green color.
No, sir, you need to unshare first.
Acha. Okay.
Okay, go to the. Yes, sir. Now share it. While sharing, select the leftmost panel. Click share.
Left.
Click share. First click share. You can see at the bottom 3.
Okay, share. And what should I do now?
Go to the bottom. Bottom panel is there. You can go to the extreme left, sir. There is a glass type is there. Left.
Okay. Top view.
No.
Okay, now I think, sir, it will come. Now you go to the full screen, sir.
It's okay?
It's okay, sir. Now,
okay.
Go to the next slide, sir.
Okay.
Next. No, it is not full screen.
Go to the next slide, sir.
This one?
Okay.
This one. Is it okay? Why?
No, sir. You can go to the bottom panel. There is extreme left. There is a line is there. Left to that line, there is one glass type is there. In the top of the
task view.
Raju sir, it's okay. We can read the content in the slide.
Yes.
Yeah, we can read it because there are no figures. So he can navigate to the slides by clicking the individual.
There are no figures. Dr.
Yeah.
Yes, sir.
You just click your cursor on the left side slides, so that you can navigate through the different slides.
Thank you, sir. Thank you.
Okay.
So this is the work what I mentioned in the past research, and this is the Monex 79 data was used at that time, which was a very novel data available. And after that, what we did the 10 degree grid at that time was chosen, and period was from 27 June to 6 August, and 25 degree north to 85 to 95 degree east were computed. That is the Bay of Bengal region was given, and the time series curves were plotted for the cloud fields. Also, the kinematic features of typical disturbed phases from 5th to 7th July were studied in Lagrangian frame by using drop-in sounded data of US research aircraft. The data profiles of U and V were drawn to identify the evolutionary feature of severe thunderstorm cell associated with the monsoon depression, and to the two plausible models of thunderstorms were postulated in terms of cluster coalescence theory and giant cluster theory. This work completely has been published in the Mossam 1990 with all satellite imagery analysis and the pictures. And this is all both the theories with the models and results as well. Now coming to the next study, in 1992, we investigated the Northern Hemisphere Conference Zone, and we found they were greater in size and greater in intensity and longer in lifetime than of Southern Hemisphere Conference Zone. And this was also found that this was due to the higher sea surface temperature favored their formation. So this was second study which was presented in Met 93, and finally this one of the selected paper was taken by Dr. Datta in his book Advances in Tropical Meteorology, published in 1996 first time. So this paper, all the result of this Southern Hemisphere and Northern Hemisphere Conference Zone with the results, with the imagery can be seen in that published work as well as the published book. Now coming to the present thing, now with the progress of the satellites and the remote sensing techniques, and when we came to the geostationary satellite, and further the latest which we all know that now we are trying to work on this satellite fitted with lightning sensor, future constellation of CubeSat carrying high frequency passive microwave sensors. These were analyzed, and a movie loop. These all were analyzed in the movie loop sequence on a computer controlled storage display and processing device called McIDIS. That is Man-Computer Interaction Data Access System. Next, 3 to 6 hours sounding surface and drop sound analyze in time section of temperature, anomaly, humidity, and equivalent potential temperature. The integration of satellite and surface sounding data would be accomplished. Now, this is under study is going on. The Percival model in which the section strips are treated as a space section. We have reduced the grid, which was 10 degree, 10 degree. We have reduced the grid to 1 degree by 1 degree to meet the numerical weather prediction model criteria. The canary feature of these disturbed phases will be correlated with extracted sea surface temperature over the grid box 1 in 1 degree. The time series plot of 3 UT surface pressure gradient between a few selected stations falling at the almost of the same latitude and longitude in the northern hemisphere and the southern hemisphere as well. To bring out the few optimum value of these parameters, which would be used to develop medium range thunderstorm forecasting model as well as the thunderstorm numerical prediction models. Now, the research method, we also studied in the past, there's teleconnections. What is the teleconnection of the northern hemisphere equatorial trough or the southern hemisphere equatorial trough vis-a-vis your northern hemisphere conference zone and the southern hemisphere conference zone as well the IT set. This complete work is again available, which was done by DMSC, I mean the Defense Meteorological Satellite Pictures, Stylus Pictures, and later on INSAT also available in 1993 publications. The values of characteristics of lifetime, distribution trajectory, size, and three-dimensional structure, very important, three-dimensional structure with a vertical extent of these systems was computed, and now by using this latest INSAT data, I mean the geostationary satellite data, CubeSat thing, we will be using the same TRMM DBM relation through the process of this. I am talking, as you know, for the numerical prediction model through the process of initialization, computations, parameterization within 1 degree and 1 degree grid box by the computer algorithm. Now, with the latest remote sensing technology, this 1 degree grid resolution can be analyzed, can be studied, which was not possible earlier with the TIRES or the polar orbiting type of satellite. So we again propose to study the three-dimensional structure of these thunderstorms and develop medium range forecasting model and further to go to the numerical prediction model. So now what is the research methodology, and we are going to use the procedural steps for the operational medium range forecast, thunderstorm forecasting model and thunderstorm numerical prediction model would be improvements to vertical initialization and data estimation, improvement to thunderstorm peaks, increase change vertical resolution, nested domain sizes, replace operational thunderstorm models with TNPM system, three-way atmosphere ocean wave coupling, and the basin scale configuration. Ladies and gentlemen, well, all these methods are explained and well defined, and the people who are working in this field of numerical prediction model. I'm not going to take into detail these things. These are well known in the latest young researchers. And because there is a paucity of time and my sitting is becoming also difficult. So finally, the result of these mesoscale convective systems along with the internal structure studies in space and time would help to understand better the regional aspect of depressions, thunderstorms, as well as tropical cyclone storm. These tropical cyclone storm models have been also developed, and this I had presented in the international Intromet also in the past. So this is the teleconnection of northern hemisphere. Southern hemisphere will be also studies. And with this, I wish you all the best of luck, and thank you very much for giving opportunity to me.
Thank you, sir. Thank you very much for overall talking about improvement of numerical weather prediction models, starting from the thunderstorms and tropical cyclones. So thank you very much. And with this, we conclude our sessions. I think today we have covered 6 talks, starting from field experiments, monsoon processes, modeling, and subseasonal to subseasonal predictions. So with this, there is any discussion and questions to Professor Goswami, sir? Yeah. So there is no questions. So now let us thank all the speakers for managing the time and giving within this short time they are giving all these details for each talks. So now we can conclude our sessions and go to admin, organizers.
Thank you very much and God bless to all of you.
Thank you, sir. Thank you so much. Namaskar. Dr. Das.
Yeah, okay. So thank you, Dr. P.B. Rajuji, for nicely conducting this first parallel session. Both the halls, yes, were very nice. Just now I just concluded the hall A session, and now in hall B. So both the talks, both the sessions actually were very interesting talks were there. So thank you very much. And actually, just I want to announce something that today formal inauguration will be there at 16-hour IST, and that is 12:30 UTC. Followed by there will be 4 invited talks are there. So I'll request all to join again, and also those the e-poster and short oral poster, those who have given already submitted today, we will be uploading. That session will be starting tomorrow. So those who have not done yet, please do it today itself at the earliest, so that it will be available in the tomorrow morning before the session. Thank you very much again. So we see you all on a happy note. The World Meteorological Day. Secretary General also will be there. So let us see and wait for the next session. Thank you very much.
Thank you, sir.
Sir, short oral and e-posters are available in the IWM website. So
Yes.
those who are submitted, already submitted, it is uploaded. So delegates can visit those pages.
Okay. Thank you.